Hey everyone, and welcome. Today, we're going to dive into something that's at the absolute heart of being an aerospace engineer, figuring out how to see fluid flow. We're basically learning how to make the invisible visible. Understanding the different tools we use for this is, well, it's everything. So let's get right into it. So, here's the fundamental problem we're always up against. Air is transparent. You can't see it. But the way that invisible air moves around an airplane or a car is what creates lift, drag, everything. So the big question is always, how in the world do we see what the air is doing so we can actually analyze it? Now, you might be thinking, okay, find a way to see the flow and you're good to go, right? Well, not so fast. It's actually a lot more complicated than that. As you're about to find out, the way we choose to look at the flow can give us completely different pictures and totally different insights, especially when things start to get messy. So here's our game plan for this explainer. We'll start with the basic challenge, then we'll build a nice, simple foundation with something called steady flow. After that, we'll introduce our 3 main visualization tools. Then we'll see how they all behave differently in unsteady flows. And finally, we'll connect it all back to why this is so critical for real-world engineering. Okay, first up, understanding flow. And I'm not kidding, this isn't just some topic in a textbook. This is the absolute bedrock of aerodynamics. Right, so the main thing to get here is that visualizing flow is all about collecting data. These beautiful lines and patterns you see, they're not just for cool posters. They are telling us a story about the pressure, the velocity, and all the forces that are acting on that vehicle. This is how we figure out if a design will actually work. To really get a handle on this, let's start in a perfect, idealized world. Before we can understand the chaos, we have to master the simple case. And that simple case is called steady flow. So what does this actually mean? Imagine you could stand in one single spot in a river. In a perfectly steady flow, every single water particle that zips past your nose would have the exact same velocity, the same pressure as the one before it. The particles themselves are moving, of course, but the overall pattern of the flow is totally frozen in time. And here is the absolute key takeaway for this part. In this perfect, unchanging world of steady flow, all 3 of the visualization methods we're about to talk about, Pathlines, Streamlines, and Streaklines, would look exactly the same. They would be completely indistinguishable from each other. Burn that into your brain because everything's about to change. Okay, so let's leave that perfect world behind. The truth is, most flows in the real world are unsteady. Think about the turbulent air churning behind a landing airplane. For situations like that, we need 3 different tools to get 3 very different perspectives on what's happening. First up, the Pathline. This is pretty intuitive. It's the life story of one single particle. Imagine you could put a tiny little GPS tracker on one speck of dust and just follow it on its entire journey through the air. The line it traces out over time? That's its pathline. This is what we call a Lagrangian description. You're riding along with the particle. Next, we have the streamline. Now, this is totally different. It's not a history of one particle. It's a snapshot of the entire flow at one frozen moment in time. It's like you hit the pause button on the universe. A streamline shows you which way the fluid is heading at every single point in space, right at that instant. This is an Eulerian description. You're standing still and watching the traffic go by. And finally, we have the Streakline. This is the one you've probably seen a million times. Think about a smoke wand in a wind tunnel. It's sitting in one spot, just constantly releasing smoke particles. At any moment, the Streakline is the line you get by connecting the dots of all the particles that have ever come out of that wand. Okay, so we have our 3 definitions. In a steady flow, they're all the same. But what happens when the flow is unsteady, when the velocity at every point is constantly changing over time? Well, this is where it gets really, really interesting. This quote from Anderson's textbook just nails it. When a flow is unsteady, these lines start to go their separate ways. And understanding why they look different is absolutely essential to knowing what you're actually looking at. So let's look at the classic example that really shows this. On the left, you see pathlines. On the right, a streakline. They look completely different, even though they all start from the exact same point. So, what is happening here? Okay, here's the best way to think about it. The streakline is like a conga line of particles. The particle way out at the front of the line left the starting point a long time ago, when the flow was pointed in one direction. But the particle at the very back of the line, right near the origin, just left a split second ago, when the flow is pointing in a completely new direction. The streakline is the snapshot connecting all those different particles in their different positions, and it shows you the history of how the flow direction has changed over time at that single point. So let's pull all this theory back into the real world. Why do we, as aerospace engineers, have to care so much about these picky definitions? This little table right here is your cheat sheet. Honestly, it's a great way to lock in these ideas. A pathline is Lagrangian. It's the history of one particle. A streamline is Eulerian. It's a snapshot of the whole field. And a streakline is what we see in experiments with smoke or dye, showing us a collection of particles from one spot. And this brings us right back to where we started. When you see this iconic picture of a car in a wind tunnel, what you are looking at are streaklines. And here's the crucial part. If that flow is unsteady, you have to remember that those lines of smoke are not the path a single particle is going to take, and they're not an instantaneous picture of the whole flow field. And this isn't just for wind tunnels. In the modern world of computational fluid dynamics, CFD, your computer can plot any of these lines for you. So if you're simulating something complex and unsteady, like the airflow around a helicopter's rotor, and you ask for streamlines, you have to know you're only seeing one frozen instant. Asking for a streakline might give you a completely different picture. And if you get it wrong, you could make some huge mistakes in your design. So I'll leave you with this final thought to really chew on. Picture a plane coming in for landing. As it deploys its flaps and lowers its gear, the airflow around the wings becomes incredibly unsteady and complex. Now think about the little vapor trail that sometimes forms at the wingtip. That's a real-life streakline. How do you think its shape would twist and change in real time to show that changing flow? That's the difference between textbook theory and reality, and it's what makes this stuff so cool. Thanks for tuning in.